In today's video, we're going to be presenting a proof that artificial intelligence, AI, cannot be self-aware, and hence providing proof of the existence of the human soul. I'll be presenting this from the perspective of a scientist and atheist, which I was for many years, as well as that of a recently born-again Christian. So, let's begin. First, we're going to present a mathematical theory which we're going to use today called mathematical induction. Mathematical induction is a method of proof that allows one to demonstrate or prove that a proposition is true for infinitely many cases without having to construct infinitely many proofs. In fact, we only need to show two proofs in order to prove that the proposition is true for infinitely many cases. And this works as follows. First, we prove the proposition is true for what we call a base case, which can be represented by the number 1. Secondly, we prove that if the proposition is true for some integer k, then it must also be true for k plus 1. Once we've proven both of those two things, we're done. We've effectively proved that the proposition is true for infinitely many integers k, in fact, every k greater than 0. So we're going to use this today in our proof that AI can never be self-aware. Let's now touch on a little bit more theory. Here we're going to be talking about the mathematical model, which is most commonly used in AI. Now, this model is called the artificial neural network, or ANN, and it is comprised of a series of layers of elements. The first layer is called the input layer, and as its name may imply, these are the features or the inputs into the neural network. So this would include things that you can see in the real world. So maybe its color of an object, its weight, its texture, its shape, its temperature. And so there are a number of these different features which can go into the neural network, and they are visible in the real world and measurable in the real world. Now, those features talk to the second layer in the neural network. The second layer is called the first hidden layer, and this is comprised of neurons. And there are arbitrarily many neurons. In this example, there are R neurons. So they're represented here as N1 through N sub R. Now, when we say that each feature talks to or is connected to each neuron in the first hidden layer, what we mean is there are network weights which describe how much weight a given element is going to have in influencing the given element in the subsequent layer. So for example, N2 in the first hidden layer, then how many network weights connect to N2 from the layer above? Well, in a fully connected or dense neural network, which is sort of our base case, which we're talking about here, there would be k network weights connecting to that. And in fact, the network weights for each element in the input layer is represented as an R tuple. That is to say, a vector of dimension R, which allows each feature to influence potentially every one of the R neurons in the first hidden layer. Now, just like we talked about how the input layer could talk to the first hidden layer actually can influence, of course, the second hidden layer, etc., all the way down to the last hidden layer. And there can be arbitrarily many hidden layers. In this example, we represent that number of hidden layers as M. And then going from the last hidden layer to the final layer in the ANN, we're moving back out to the real world again. So here we have what's called the output layer. And these are not input features anymore, but they're just output variables. And so, for example, it can be, and these can be different variable types. So there might be a binary variable, for example, so a 0, 1, where 1 represents a diagnosis. And maybe the input features were features of, say, an MRI or something. Or perhaps the output could be a nominal variable, so unordered categorical. Maybe you've got a driving program, a simple driving program where a robot can go forward, backward, left, right, and that's it. So that's an unordered categorical. And then you can also have continuous outputs as well. Now, one more aspect of the artificial neural network, in addition to the network weights, is something called the activation functions. So when you have a bunch of features in your input layer talking to, say, one neuron in the first hidden layer, let's say N2. N2 has an activation function. And so that activation function, in combination with the values of the input layer, also in combination with the network weights connected to N2, all determine whether or not N2 fires. You think about a brain and neurons firing. And then carry that forward to the subsequently down throughout the hidden layer. So you've got network weights and you've got activation functions. Now the network weights need to be estimated. And we can estimate those through various methodologies, and probably two of the most commonly discussed or utilized would be gradient descent or backpropagation. And with artificial neural network, backpropagation is pretty much the standard. And this is where you move forward through the network, doing network weight updating. Then you move up backwards with a different mathematical process to update them again. And you continue this forward and back propagation process until the weights no longer change, or hardly change at all. They don't change within some epsilon, some very small number. And then it's considered that the network has converged. And at that point, you've trained your neural network you've optimized it in order to provide really good predictions for whatever your output is. Let's just call it Y. And what is a good prediction? Well, you might go by accuracy, so percentage correct. There are other metrics such as things called sensitivity, specificity, but we're not going to get too down into the weeds in the various other metrics. Just think about it as you've trained it to be as accurate as possible. And now you're ready to use it to make predictions. So we've talked a little bit about the theory of an artificial neural network, and it might have looked a little daunting. So let's just reduce that feeling a little bit and demonstrate how few lines of code are required to fit one of these. And in fact, you could fit a fully connected dense neural network and call it 8 lines of code. So shown here are 8 lines of code, which can be run just on an old laptop. This doesn't require some supercomputer to run this. Of course, it is dependent on the size of your input data set. But generally speaking, you can run these things on laptops. And effectively, this is what's shown here is the Python code with the Keras Python library fitting a fully connected, or otherwise known as a dense neural network, and then training that neural network on a test data on a training data set. And then not shown here, but an additional step would often be to assess its predictive utility on a validation data set. But once you've trained it, you can then use it to make predictions. And what we've shown here is that we're actually doing that for every day over the course of a year for a simulated 50-year-old female. And the only variable we're having day to day here is going to be whether or not it's raining. And we're representing that as a 10% random probability. And it may be that in your training data set, it was the case that on rainy days, people were less happy. They had lower probabilities of being happy. So that should be reflected in the model predictions. And then we're just going to print out the results. Happy on day 1, question mark, happy on day 2, question mark, and then for each of those, it'll be a 0 or a 1. And then looking at this and understanding how basic this is and simple, I would then pose the question, is this program running on this old laptop self-aware? Now the answer should be no, a resounding no. And it's not that it's a little bit aware, it's maybe having a vague dream. The self-awareness coefficient of this particular 8 lines of code running on your old laptop, this clearly has 0 self-awareness. So that is in fact our first step in the mathematical induction we talked about earlier. So let's go to the second step. The second step, we say, okay, so given that the proposition is true for some k, in this case 8 is k, can we show that given it's true, and the proposition being true means that it's not self-aware. That's the truth that we're demonstrating here. Is it also true for k plus 1? So let's add 1 line of code. Let's make it 9 lines of code. So we're just going to add an additional hidden layer here with 100 neurons and the activation function of ReLU. And that's it. It takes a pretty small line of code. Do you believe there's any possibility that that additional line of code has changed the self-awareness of the original unaware neural network running on an old laptop? Now, it should be clear just by looking at what is involved in coding this and that understanding it's just math, it's just computer code, and it's just optimization, mathematical optimization, that the self-awareness remains 0. And so this is step 2 of the mathematical induction, showing that starting from an unaware ANN, adding a single line of code will not change it from unaware to aware. Okay, so adding lines of code is not going to change the self-awareness, but what if we made it not look like an old laptop anymore? What if we took that CPU and we removed it from the laptop and we inserted it into a robot head? So we put a motherboard in a robot head, power supply, but we just made our computer case look like a robot with a smiley face. And it could either smile or frown depending on the rain. And instead of showing 0s or 1s on a screen, it would just smile or frown. But the code is identical, the CPU is identical, everything's the same, just the robot itself, and 0 or 1 is now smiling or frowning. Is that now self-aware? Does that change the awareness of the code? It's obvious the answer is no. So we have a robot now that smiles or frowns every day based on the weather, and it's for sure this is not self-aware. Okay, so let's add some more functionality then, because thus far it's been a pretty simple robot with pretty limited functionality. What if we gave it the ability to see? Well, that sounds pretty impressive, doesn't it? But what does it mean to give a robot the ability to see? It pretty much involves a class of artificial neural network called a convolutional ANN. And a convolutional ANN is very similar to the fully connected or dense ANN we saw earlier, except that each input feature no longer affects all the neurons in the first hidden layer. It only affects a region of them. And I want you to think about it as a given point in your visual field only impacts a small number of nerves, not all of the nerves. Or looking at it the other way around, a given nerve bundle in your retina only has to process a relatively small cone within your broader field of vision. And the purpose of limiting the connectivity and not having a fully connected neural network when it comes to vision is to reduce the burden of the brain having to process such enormous amounts of information. There's a lot of information in a full visual field. And you can actually have a very effective neural network just by having each nerve bundle, or each neuron as it were, only processing a very small number of features, and having then those neurons in that first layer continue to talk to the second layer, etc., down to the nth layer as before, and then to the output layer, which might be some decision in your mind as to an identification of an animal or a threat or a food source or something else. And so that the impetus for the convolutional ANN was actually an analysis of biological brains, but that shouldn't change your understanding that when it comes to implementing this on a laptop computer, it's just math, which is very understandable. It's exactly the same as what we reviewed earlier, except it's less connected. That's all. We've removed some network weights. That's it. And the lines of code is very similar. It takes maybe 5 or 10 additional lines of code, and you've got a very nice looking convolutional ANN, which is set up on your laptop. Okay, great. So now your robot can see. What about chatting? You know, there's all these fancy chat bots now, right? There's ChatGPT, and I think Microsoft has one, and there's tons of them now. And they're all called, you may have heard of this, called large language models. Large language model is a specific subcategory of what's called a recurrent artificial neural network, which itself is a subcategory of artificial neural network. So the recurrent ANN takes and analyzes sequences, and it will analyze and predict words based on earlier words in a sentence. So you might feed it 5 words and ask it to finish the sentence for you, and it can finish it pretty convincingly once it's analyzed the data appropriately. And then if you ask your chatbot to write a letter for you, it seems like it can write a pretty coherent letter. And the way it's doing that is it's actually analyzing sentences that follow other groups of sentences, and then paragraphs that follow other groups of paragraphs, and finally even potentially chapters that follow other groups of chapters. So you can, if you have enough input data, you can train a large language model, i.e. a recurrent artificial neural network, to write books for you pretty convincingly. And it looks like it can think. Boy, that must take millions of lines of code, right? No, actually, it's 5 or 10 lines of code and gigantic source data sets. And that's really what's hard about it, is you've got to train it on these gigantic source data sets. So the training can take a lot of computing power, but once it's trained, running it can easily be done on a laptop CPU. So the computing power to run this thing is quite comparable to what we had before. The number of lines of code is comparable to what we had before. And all of a sudden we have a robot that can laugh and cry and see and talk to you based on what it sees. But when we understand what it took to get to this point, which is add 5 lines of code, and then train it, it should be clear that this is exactly the same as what we had before with respect to self-awareness. In other words, zero self-awareness is going in, is still zero self-awareness after adding these additional modifications, because they involved a couple extra lines of code, and we've already demonstrated step 2 in our mathematical induction. So we have a very convincing AI now running in a robotic body, which we've pretty much now understand to not just have limited self-awareness, but to actually have zero self-awareness. And in fact, regardless of how complex we make this, we can add more lines of code that do other things. It's all mathematical models. The logic alone does not make the self-awareness. So let's put this together in the form of the mathematical induction. So we started with 8 lines of code. It was a simple ANN, and it was very obvious that this is not self-aware. That was our proposition base case. We showed that adding one line of code clearly doesn't make it aware. If it was unaware to begin with, it remained unaware. And then we just repeat the above step ad infinitum in order to conclude that AI, regardless of how complex, can never be self-aware. So what do laptop CPUs and robots not have? And what, in fact, can they never have, which humans do have, that allows humans self-awareness? It gives us awareness and consciousness, while the robots can never have it, regardless of how complex these mathematical models and computer codes get. And the answer, of course, is the human soul. So once we have convincingly proven that regardless of how convincing an AI might be in pretending to demonstrate emotion and pretending to, or in fact carrying on a conversation with you, you're literally talking to math and lines of code. You're just talking to a bunch of logic. And when you understand that, you finally realize that not only have you proven AI can never be self-aware, but you have at the exact same time effectively proven the existence of the human soul. Let's go now to the scripture. Let's go to Genesis chapter 2, verse 7. And the Lord God formed man of the dust of the ground and breathed into his nostrils the breath of life, and man became a living soul. Next month, we'll cover another topic. I try to do about one topic a month, oftentimes from the scientific atheist perspective, as I was for many years, as well as the newborn Christian perspective, as I am now. And I hope you can join me then. Thanks for watching Evidentiary Christianity. If you want to help support us via Bitcoin, that's our Bitcoin address right there. Please like and subscribe, and I'll see you next time. Bye-bye.